Welcome everyone to our ilifu online training workshop. Thank you for joining us today. We'll be presenting the first of 4 sessions today, which will provide an introduction to ilifu, and then we'll follow this with 3 more sessions over the next few weeks that'll expand on the introduction and they'll cover more advanced topics. I'll start by introducing the ilifu support team. So Walter Salima is our astronomy support specialist, and Dane Kennedy is our bioinformatics support specialist, and Theo Matsapane is our systems administrator. Theo, if you want to wave, cool. And Theo also provides user support, and then myself, I'm Jeremy. I'm the ilifu operations manager. So please note that the training sessions are being recorded. We'll make these recordings along with the presentation slides available from the ilifu website as a resource for everyone to use. And we also go through a few demos during the presentation, and we've created a GitHub repo to store these demos so you can use them as tutorials. We'll post the link in the Zoom chat. Otherwise, the link can also be found in the slides later in the presentation. So the topics for today will be an introduction to the ilifu facility and its primary services. We'll go through the cluster's directory structure and talk about available software environments, and then introduce the 2 main services that most users are interested in using, and that's Jupyter and the ilifu Slurm cluster. And Dane will present on an introduction to Slurm today. We cover quite a lot of material, so we're going to push through the presentations, and then we'll host a Q&A session at the end of the workshop where we can address any questions that you might have. You're welcome to post questions during the workshop in the Zoom chat, and the support team can address them in the chat at the time that you ask them. But otherwise, we can also respond to your questions in the Q&A session at the end of the workshop. So before we start, I just want to point out the available support channels and where to find information about ilifu services. You can email the support team at support@ilifu.ac.za. We have a ticketing system and our team of support personnel who will respond to any questions or issues that you might have. Our user documentation is available at docs.ilifu.ac.za. I'm just going to flash this up to give you a demo. So it's broken down into a step-by-step guide on how to use ilifu under the Getting Started section. And this is from requesting access or account, changing your password or using or how to generate SSH keys, all the way down to the directory structure, submitting your first job on Slurm using Jupyter. A lot of these topics are expanded upon under under technical documentation. And then we also have domain-specific information for astronomy and bioinformatics, and then specific section on data management for transfers and data management. We do update the documentation regularly about new services or expand on sections, so we recommend or invite you to come and look at the documentation or use it as a reference as much as possible. And then going back to other support components. So we have a status page at status.ilifu.ac.za, and I'll just also flash that up. So this just provides the current state of the cluster. So you can refer to the site if you experience any issues. This is a good place to come and look. There's a general status at the top of the page, and then the status of different components are listed below. So these are drop-down menus that you can expand on and see what the status of the cluster is. So if there's an issue that we pick up, we'll report it on this page. We also provide information about incidents, and you can see past incidents below. Anything current will be at the top here. And we also might indicate maintenance periods on this page too. And then the last 2, the training videos. So as I mentioned, we record these videos, the presentation slides, and the videos are available from the ilifu website under latest training. So the full set that we recorded or hosted in September are already available here, along with the PDF presentations. And yeah, the demos are available on our ilifu GitHub, which you can download. So before we get into ilifu, I just want to cover some general concepts related to high-performance computing. When we talk about high performance computing or HPC, we're talking about combining a bunch of computers or compute servers over a high-speed network for greater processing power and speed to solve complex problems. And these are typically problems that wouldn't be able to be solved with an ordinary or even a high-end desktop or single workstation. Another reason why you might want to access an HPC environment is to access large data that could not be stored on your personal workstation on account of the data size. And then some just general terminology, we refer to a server as a node, so a compute server is a single node, and then a collection of nodes in a pool we call a cluster, and we might often refer to the ilifu Slurm cluster, so that's our pool of compute resources that's available for users to use. So ilifu is a cloud-based facility for data-intensive research in the fields of astronomy and bioinformatics. We provide users remote access to high-performance computing resources, storage, and other services that support a range of projects and requirements. We use open source cloud software to manage a flexible environment, including the ilifu Slurm cluster and other services. And we also have a large focus on data management, both storage and transfer, given the amount of data associated with many of the projects that we support. In terms of accessing ilifu or using the services, there are two main methods of interacting with ilifu services, either via a command line interface using a shell terminal or through web applications, which you would access using a browser. If you want to submit jobs to the large pool of resources in the Slurm cluster, you'll want to use the terminal interface to connect remotely to ilifu. Via a terminal, we use SSH or a secure shell, and the authentication method is managed using SSH keys, which I'll touch in more detail shortly. So on the left of the slide is an example of terminal access, and the command below is how one would SSH to ilifu from your local workstation, either to the Slurm login node or a server dedicated to transfer nodes. So that's SSH and then your username at slurm.ilifu.ac.za. So once you've SSH to ilifu, you can run typical Linux commands to navigate the file system, browse directories that you have access to, edit files, and the main purpose is really to submit jobs to the cluster and monitor and manage your jobs from the Slurm login node. On the right of the slide is just a screenshot of the application dashboard that is part of the Idea Science Gateway, which is a portal for accessing all the web applications that we host using a web browser. And the gateway address is gateway.idea.ac.za. So the Idea Science Gateway makes use of a single sign-on or SSO, and this essentially allows a user to sign in once into the application dashboard from which you can access a number of different web applications, including Jupyter, Carter, Globus for transfers, an SSH key management tool, and other useful tools and sites. And this is without having to log into the individual services, which is where the single sign-on comes in. We've also recently included Visual Studio Code, another popular development environment, and this is available as an application from the application dashboard. I'll demonstrate using this when I demonstrate Jupyter later on in this session. And also note that a number of the services can be accessed directly using their respective URLs. So a lot of kind of legacy users are used to this since like pre-gateway days. So you can access the services directly from the URLs like jupyter.ilifu.ac.za or carter.idea.ac.za. So a brief note on SSH keys. Most people don't have to deal with SSH keys until you need to use an HPC or a remote environment. So this can be a bit of an initial stumbling block for a lot of users. In order to access the terminal environment, we use SSH key authentication. An SSH key is an authentication method that grants you access to a secure shell connection between your machine and a remote machine, such as ilifu. So it allows you to interact with the cluster over the internet, basically. So you'll need an SSH key on the particular workstation that you're using to access ilifu, and these keys need to be associated with your ilifu account. When you create an SSH key pair, you create a private key and a public key, and you provide us with your public key on signup, or if you're updating your SSH keys through the management tool, you'll add your public key. And it's important to never share your private key. And this is for security reasons. If someone has your private key, they can pretend to be you accessing the cluster. So never ever share your private key. And when you access ilifu over SSH, your private key on your local workstation is compared to your public key that's associated with your ilifu account. And if they match, you'll be granted access. If you haven't generated an SSH key pair on your computer before, you'll need to do that in order to use ilifu. Another reason to generate a new SSH key would be if you got a new computer, or if you want to access ilifu from an alternative computer, or perhaps you formatted your computer and you've lost your SSH key. These are reasons why you might generate a new SSH key. Each computer needs a unique SSH key so that our system knows which computers to allow a connection to it. There's very good information about how to generate SSH keys on different operating systems at this link from GitHub, and it's also linked in our user documentation in the section on SSH. And then, as I mentioned, included in the Idea Science Gateway application dashboard, there's a link to an SSH management tool. I've also indicated the URL at the bottom of this slide, and users are able to manage their own SSH keys that are associated with your ilifu account. You can add or remove keys from your ilifu account when necessary using this link or using the tool in the application dashboard. So I've included this slide just to show example of the shell environment. So SSHing to the Slurm login node and running some typical Linux commands. So starting from the top, from your local workstation, you'll run SSH followed by your username at slurm.ilifu.ac.za. If you're successful, you'll be presented with a welcome message, but you'll also see that the command line prefix in your shell terminal will have changed to indicate that you're on the Slurm login node. You can then run commands within the shell environment on the ilifu cluster. You can list your current path or show your current path using the pwd command, which is print working directory. You can list the contents of your current working directory with the ls command. You'll see a symlink or a shortcut to your workspace. New users will see a readme.md file, which has helpful information to get started with. And then the final example here is just listing the contents of, for example, the projects folder for the idea projects. So these are just some basic Linux commands. So on that note, we're going to move on to the directory structure that we use. So we place a lot of emphasis on the correct use of the designated storage spaces or directories in order to economize disk space. And this is because there's a lot of data moving through our cluster, like thousands of terabytes, basically, or petabytes. But also, the importance of this is so that storage is used properly or at least storage is accounted against projects properly. So we put emphasis on the correct use of storage locations. So we'll cover the directory structure. All users have access to common folders. Each user will have a directory in /users, and this is also known as your home directory. And then every user will also have a folder on the Scratch mount. So this is currently Scratch 3. A user's home directory is limited to 200 gigabytes and is only ready for small files and scripts and logs. And then the Scratch 3 folder is designated for processing and is for short-term use only. So you can place data here while you're processing and have your outputs written here, but this space should be kept relatively clear. When you've completed processing your data, it's important to clear files that you no longer need from the Scratch 3 spaces, move files that you do want to keep to a relevant project folder, your workspace for longer term storage, and clear any intermediate files that were generated during your processing runs. And note that we now have a 90-day Scratch storage auto deletion policy on ilifu. We scan files on the Scratch 3 mount and alert users or affected users about files that are older than 90 days and that these files will be removed at a specific date. So we send email alerts to relevant users on the second and third Tuesday of every month, and then the deletion of all files older than 90 days happens on the fourth Tuesday of the month, which is incidentally today. And then the remaining storage is split up by the larger groups. So IDEA, CBio, ilifu. There's a few others too. So I'm going to go through IDEA as an example, but really they all share very common structures. So looking at the IDEA directory structure as an example, a user in the IDEA group will have a folder at /idea/users. A user will also always belong to a project and have access to a project directory at /idea projects. And then there may be other folders that contain data, raw data or software. For example, your folder at /idea users, this is your private workspace directory, and you can store data that you perhaps don't want to share within the project folder yet. Perhaps this is test data, or it's a work related to your thesis, or you can place, it's a good place to place virtual environments in this location, and it's limited to 10 terabytes. The project folder is generally for sharing data and project resources within project groups. So key project activities and output should be stored at this location. Raw data associated with projects is also accessible from the project directory. Raw data for the IDEA group is generally read-only to prevent modification or deletion. And then there's also the software folder, which will contain software containers associated with IDEA or other IDEA specific software like the pipeline process Meerkat, for example. So as I mentioned, there's a very similar structure for CBio and ilifu users. The exception with ilifu is that the projects are further broken down into Astro-specific projects and bio projects. And for CBio, the raw data or the databases aren't linked from project folders. They're kept in a separate a DB folder and managed by the CBio team. So I put together this diagram to describe the recommended workflow on ilifu in terms of that directory structure that I've just talked about and when to use what mounts. So long-term data will generally be kept in the project directory in a user's workspace or in a directory specific to storing a read-only data such as a raw data directory. Then when processing data, you'll generally read data from these folders and then you'll output your processing or write your results to your Scratch folder. And then once the processing is complete, you'd want to selectively copy the files from the Scratch folder back into longer term storage, either the project directory or to your personal workspace. And then you'll want to remove any intermediate files from Scratch, freeing up the space for other users to use. Note that different projects and users will have different processing or data requirements. So maybe your project doesn't generate a massive amount of data as part of some reduction process. If so, then perhaps you don't need to use Scratch storage. Perhaps you're a master's student and you're just generating cutouts of galaxies for input into a machine learning algorithm, and the footprint of your data isn't large in the 100 gigs. Then work and process within your workspace directory. The main two reasons to use Scratch generally is that it's often high performance storage, such as SSDs, and this allows high performance processing in comparison to other storage that is used for longer term storage, or it's used when a computation requires a large amount of temporary storage, but only while processing. So a lot of the temporary intermediate products can be quickly removed after some level of quality assessment is completed. So make use of these resources depending on your requirements. And if you have any questions, do contact us through the support channels for help or for clarification. Okay, I'm going to move on to the software environment. We have three main environments that we support on the cluster. So there's Singularity containers, software modules, and then virtual environments. I'm going to focus on containers and modules today, and then we'll touch on virtual environments in the next workshop session next Tuesday. So containers are fully encapsulated software environments. You can think of them as a compressed folder, but they contain everything that an application needs to run, or a suite of applications. So an operating system, the application binaries, libraries, environment variables, these are all bundled into a single file called an image file. Containers are really beneficial because they're easily portable. You can copy them to and from ilifu and share them amongst project members or larger work groups. Some of you may have used Docker before, so Singularity containers are very similar to Docker containers, but they're safe for a HPC environment because they don't allow elevation of privileges when running the container. So this diagram just shows how Singularity containers kind of sit on top of the general system. So the container is the little box on the right of this diagram in the dotted line, and it may contain one or multiple applications. The useful part of this illustration is just showing that with the Singularity installed on the system, you can interact with containers using the container launcher, and that the container environment can interact with the file system outside of the container. So for example, when processing your data with an application that sits inside a container, that container environment and application will have access to the same directory structure that you have access to outside of the container. For example, the container software will have access to the scripts in your home directory, for example, or the data in your project directory. And another benefit of containers is that they can be built using a range of operating systems, including legacy operating systems. So if you're using some legacy software that has kind of older requirements, containers are quite flexible. So they can be encapsulated in this container and still run on operating systems that we have available on the cluster. So we support a variety of containers. The list here is mostly astronomy containers. For example, the CUSA software container for radio astronomy, data reduction, and to produce radio images. But there are also bioinformatics containers available with R and RStudio and other software. We do offer to help you build containers with the software that you need for your workflow. So if you need a service, please do contact us through the support channel for help. And I'm just going to briefly touch on how to use Singularity containers. So there's really, well, there are multiple ways, but the two ways that are kind of commonly used on the cluster is to either use the container interactively or to execute software through the container, and that's how you would do it in a Slurm script. Dane will demonstrate this later. So interactively, what you do is you can shell into the container environment using the shell command, Singularity shell, and this will place you inside the container in a shell environment with all the software and environment variables inside the container available to you. And this allows you to interact with the software via command line. This is a very useful way of debugging issues or testing what the software inputs are, for example. Alternatively, and this is, as I mentioned, how you submit jobs to the cluster, you can execute a script using this Singularity and the exec command. And you have to specify the container you want to use, and you just specify the software inside the container and any script or input parameters that you need to pass into the software. So in this example, I'm running Singularity exec. I'm pointing to the CUSA 6 container that's located in the idea mount in the software containers folder. Inside CUSA 6, it's now Python-based, so we're running Python, and I'm passing in my script.py as an example of running a container. Yeah, and then I guess just for information, it's helpful sometimes to view what's inside a container, so you can run Singularity inspect -d and the path to your container, and this will actually show you how the container was built, all the steps. So it's helpful information to indicate what is included inside a container. I'll go through a demo of this in a bit. So in addition to the Singularity containers, we also provide modules. These are software packages that you can load into your environment, for example, when submitting a job. So rather than running a software using containers, you can load a module into your environment and use that software to run as part of your job. Most of the modules are common programming languages such as Python, R, Julia. There's a large number of bioinformatics software packages that are available as modules rather than containers. And then some modules are also just shorthand for calling containers, such as the Casa modules and the RStudio modules. They have containers under the hood, but they're just modules that kind of make it easier. Modules are divided into different categories, including common modules. So this will be Python, CUDA libraries, MPI, that kind of thing. And then there are modules that will be specific to astronomy and bioinformatics domains. You can view what modules are available by running the command shown at the top of this slide. So module avail, and that'll print out all the modules. You can also, for example, filter this by writing module avail and then a specific software like Python, and then it'll just show you what versions of Python are available. And then just in terms of the output here, the capital D just shows the default module that will be loaded if you don't specify a version. So this will generally always be the latest software version of a particular software. So other useful information associated with modules, you can run the module help and then the module name. This will output some information about the module. It also might describe aliases that become available once the module is loaded. You can load a module using the module load and then specify the module with or without the version number. Module add does the same thing as module load. You can list the currently loaded modules using module list, and you can clear or remove all your currently loaded modules with the module purge. And you can also look at the help information for the module binary using the -- help. And it is also possible to load multiple modules at the same time of different software. Okay, cool. I'm gonna switch to a demo before continuing. So I'm going to start with sshing to the Slurm login node. So I'm going to do module avail, and it'll output a whole load. You can see they're broken up into Astro and Bio. There's a long list of Bio modules and then common modules. So similarly, I can do module avail Python, and it'll show me just the Python modules that are available. Just an example of the help command. So here I'm just going Casa as an example. So this just outputs what the Casa 6.6 module does, and it also kind of indicates what aliases are available to use. So there's helpful information about different modules. And I'm just going to show you an example of how when a module is loaded, it changes your environment. I am doing this on the Slurm login node, and our best practice is to not run any software on the Slurm login node. So generally, you won't load modules here. You would load them as part of jobs or on a compute node. But just to show you the difference with the environment, I'm just going to do which Python. You can see it's pointing to the system Python, which is 3.10. So if I do module load Python, an example 3. Let's do an older one because we need to install some legacy Python packages. If I now do which Python, it shows that I'm now using the Python that exists or from that module specifically. And if I do Python version, you can see that the version has changed. So that's how simple it is to use or load modules into your environment. I can do module list to show you what we have loaded. Singularity is just loaded by default. I'm going to purge the list and relist. So you have no modules loaded. And I'm going to demonstrate Singularity quickly. So let me just load Singularity again. I would normally do something like Singularity shell, etc. But if I run Singularity, it's going to put out a message saying that you can't run Singularity on the login node. And this is specifically because we don't want software run on the Slurm login node. It's a small node and should just be used for job submission. So I'm going to pop myself onto one of the development nodes. We'll go through this in a later session, but just as a part of the demo. So if I do Singularity, I can now run Singularity fine. So I'm going to shell into, well, let me first do an example. We don't install software on all the compute nodes because I would bloat it. So if, for example, I can't uh, auto-complete these common astronomy softwares. So I'm going to do Singularity shell, and I'm going to go into a very commonly used astronomy container. So this container holds a suite of astronomy software. And now I'm shelling into the container. You can see that the command line prefix has changed. And now I can, for example, autocomplete, and here's P Segale and Sophia, for example, they're available for me to use because they're in the container environment. And I can, for example, what's the Python version? And here will be different too. It's the Python inside the container. And then similarly, so that's the shell command. If I do Singularity exec and idea software containers, same container. And I'm going to use the exec command. So here I want to specify the software that I want to use, and then I'm just passing in, here is just a command, but I could pass in a script or parameters that I want to run using this container. So here I'm running Singularity exec, pointing to the container, running Python. I'm just asking Python to print hello world. And so this is outputting hello world, but using the Python that's available in that AstroPy container. So those are kind of simple ways of using containers and modules on ilifu. Okay. So finally, JupyterHub. This is the web interface that we use to spin up a Jupyter session that you can use for development. So this is the from the gateway, you'll click on the application dashboard and it'll bring up your the login page requiring your username and password associated with your ilifu account. You don't require an SSH key to access the Jupyter web environment. You can access the service from anywhere, just from your just using your ilifu username and password through a web browser. And in fact, you can also link your institutional account to your ilifu account using the edugain/sapphire. So if you're from UCT or UWC or UP, you can use your institute account to actually log into ilifu through this option. And then the picture on the right just shows the application dashboard again. And if you're logging in via the IDEA Science Gateway, you'll see this after logging in, and then you can select Jupyter from the dashboard. Once you're logged in, you'll be directed to a page where you can select your session size, and you can also see what session sizes are available. We have two different flavors of sessions now. We have a shared resource session type, where the CPU resources allocated to you may be shared with other users using this resource type. Then we also have dedicated resources. And this is where if you select a session size, you know that those resources are going to be allocated to your user and not shared. So we always recommend in the first case to use the development session where resources are shared. This size session generally meets most development requirements. And if you find that you need dedicated or large resources for your task, then go and look at selecting a larger session size. Generally, a large session size is only necessary if you have a memory-intensive purpose. The sessions go up in in amount of RAM available per session. I'll show you that in the demo. And then after selecting your session size, you'll be taken to the launcher page where you can select a kernel you want to develop with. The kernels can be used in Jupyter notebooks or console environments, and you're also able to start a terminal session which provides command line interface on the compute node where your Jupyter session is running. So I'm going to demonstrate this process as well quickly. Okay, so from the Idea Science Gateway, click on Application Dashboard. I'm going to log in using my ilifu username and password. So here are the different options. There's Jupyter, Carta, Globus, Visual Studio. This is the SSH key management tool. And there are shortcuts to the ilifu status page, for example. I'm going to click on Jupyter as that's part of the demo. So here you can see the different session sizes. This is the shared size or shared session type. So you get 2 cores, 3 gigs of RAM. And these, the compute resources are shared. And this is really just to optimize resource usage. If this is sufficient for you, it just means, with Jupyter specifically in development environments, generally the CPU sits idle while you're typing code and that kind of thing. So most people can get away with very small CPU requirements. If you need a dedicated session, you can see that the RAM size goes up. So if you're looking at astronomy data, which is quite large, or loading very large tables into your environment, you may need to look at larger sizes. But this is a shared resource, so please always use the minimum that you need for your processing or science case. I'm going to go ahead and select the development session. So this will take me to the launcher page. Okay, so I did have some notebooks open. I'm going to close this one, but you can come back to your previous notebooks if you exit and come back in. So this is usually where you'll land on the launcher, and you can select a kernel here. So I'm just going to, let me open up a new kernel. You can immediately start coding from a cell line. There are lots of different kernels for different, either projects have their own kernels, or there's generic astronomy or Kaiser kernels. But I also actually want to, so we have the ilifu user training. We've put together a quick reference guide for Jupyter. So it's a Python notebook, but it's also demonstrating that you can use Python notebooks for include Markdown as well as code. So you can use this as tutorial material for classes, that kind of thing. So it's a really useful resource. I'm not going to have time to go through this in detail, but basically it describes the layout of Jupyter, how cell execution works, mouse and keyboard navigation, and really useful shortcuts. So you can either go and look at this on the GitHub page, or you can download the Git repo and go through this yourself on ilifu. Other useful kind of cell functions is that you can tab complete to autocomplete function names. You can shift tab to show package doc strings if you want to get information about certain packages, which can also be printed out with the by putting a suffix of a question mark, etc., etc. So I'm going to not go through this in too much detail, but I do invite you to go through this if you're interested in a little Python and Jupyter demo or tutorial. The one thing I will point out is that even if you just close the session, it doesn't release the compute resources that you've allocated to yourself. So what's really important is once you've finished your session, you want to go to File, Hub Control Panel, And here you can stop your session and release the resources for other users to use. This is also the way you would stop your session if you wanted to choose a larger sized session. So you can stop my session, and if you to start my session, you can go back to the launcher page where you can choose a different session size. Cool. And I think that's everything I wanted to go through. So I'm going to hand over to Dane, who's going to take us through the introduction to Slurm.
Well, thanks, Jeremy. Oh, share my page. There you go. Can you see my slides?
Yeah, I can see your slides.
Cool, thank you. Yeah, hi everyone. So my name's Dane Kennedy. I've been with ilifu since about 2019, and I'm primarily bioinformatics support, and then I'm also involved with various small admin things like making sure Slurm is working every now and again. Yeah, so welcome to the session. I'm going to talk about Slurm, what it is, and I'll do some little demonstrations and show you how to do some basic Slurm things like submit a job and check how your jobs are going, and basic accounting. So first off, what is Slurm? Slurm is an open source workload manager or scheduler. What it does is it allows you to submit computing tasks, also known as jobs, to a computing cluster. A computing cluster, as Jeremy mentioned, is a collection of computers or servers, which we sometimes call nodes, and that comes together with some storage. We've got something like 8 or 9 petabytes, I think, and they're all linked together with a fast network. The workload manager figures out when and where those jobs can run and keeps a record of their resource usage for accounting purposes. From a user's perspective, there are 3 main components that you should be aware of. Firstly, there's the login node. Apart from Jupyter, or maybe Casa, this is usually your first point of contact with a cluster and the place where you do most of your interactions. It is not a server to use for big computing tasks, but rather it's a place for administrative tasks, such as submitting jobs, editing scripts, and light management of data. The login node is shared with all the users of the cluster, so any misuse impacts others negatively. So we monitor it closely and are quite strict about how it's used. So it's not uncommon for us to kill any processes you might be running there if they shouldn't be there. Secondly, there's Slurm itself, which has 3 main functions. Firstly, Slurm allocates resources to users. In other words, this is reserving memory and CPU on compute nodes for specific jobs. Slurm provides a framework for starting, executing, and monitoring work jobs. And these are the commands I will cover a little bit later. And it manages a queue for pending work. So when you submit a job, it first sits in a queue and waits for its turn to run. In Slurm, these queues are called partitions, and there are several different ones you can choose from, and I'll cover that in the next slide. And then finally, there are the compute nodes. This is where these are bigger servers, and it's the place where your computing jobs are run. Once you're running something on a node, the resources you've requested are allocated to you, and this means that nobody else can interfere with the running of your software. But on the other side of that, you should be as accurate as possible when specifying those resources so that nothing's sitting idle and being wasted. And that is covered in more detail in, I think, session 2. We've shuffled things around a little bit, so I'll get quickly into it. So this table shows a summary of the available partitions and the resources available on them. Starting with the login node. As mentioned earlier, this is where you'll perform basic administrative tasks, such as running bash and slurm commands. Then we've got the Jupyter development partition. That's these 2. Think of these as a development space for testing new software, plotting results, building workflows, and debugging. We have the main partition. This is where most stable and computationally intensive jobs are executed. By stable, I mean that the code isn't changing. It's an established process that only differs in input and output. Parallelism may be possible, or jobs may be split into small tasks. Then we have the high mem and GPU partitions. Although they're not covered in this presentation, the high mem partition is designed for single high memory jobs that can't be split up. We'll dive deeper into this topic in a later session. And while many users use Jupyter as their primary interface with the compute resources, we do, as a general rule, prefer it if users use one of the main high mem or GPU nodes, as this tends to result in more efficient use of resources. This is because interactive jobs such as Jupyter tend to have longer periods where resources are sitting idle. When running jobs on the cluster, the default partition is this main partition. And unless you explicitly need something else, this is probably the one you'll want to use. The nodes here mostly have 32 CPUs, cores. We use those terms interchangeably. Any computer scientists, you might object. And they mostly have something like 232 gigabytes of RAM available. We also have the high mem nodes, two of which are 32 cores and 500 gigs of RAM. We have very large with 1.5 terabytes of RAM, and we have one that's somewhere in the middle that's with about 1 terabyte of RAM. And then we've got the GPU nodes, I think 7 of them, and they're very similar to the nodes in the main partition, except they have 1 or 2 GPUs available, and there are various flavors of GPUs, if that's interesting to you. And then finally, just this development partition you can use for interactive jobs, and we explain that later. Yeah. So this slide shows the 2 primary ways I mentioned earlier of interacting with cluster. Jeremy's demonstrated them a little bit already. So on the left is the Jupyter interface. Thing I really wanted to point out is that on the back end of Jupyter, it's actually running as a Slurm job on a regular compute node. So we have the JupyterHub interface running as a service on its own node. It's a small little service. But that service then submits a job on your behalf and then acts as a proxy between, say, Jupyter Lab and your browser. And then the image on the right here is just what I'm going to be demonstrating shortly, and that's your your shell commands, CLI, often called CLI. But I didn't mention earlier, but these slides are all available and they're actually interactive. So you'll get that link, but I'm quite excited about the fact that you can copy and paste from these little videos. So I'm not going to show you what it does, but that's just logging in. Yeah, so then first off, I'm going to talk about the command line interface. So the very first thing one needs to do is using the SSH command, which Jeremy showed you, and that lands you on the login node. Once you're there, these are the basic commands, Slurm commands, that are useful to get you going. These commands allow you to submit or monitor jobs, as well as get information about the state of the cluster. And I'll demo all of these later, but let me give you a quick rundown. So first there's the sinfo command. This gives you information about the partition, sometimes called queues. It shows you the number of nodes available and their state, like are they free, are they partially used, or are they fully allocated to jobs. And there's the sq command, and this gives you information about all the jobs that have been submitted to the cluster and have not yet finished running. You can filter this information in various ways. For example, you can filter by user. So this command shows you only the jobs that you've run. This reveals a variable, so it'll be your username. Then we've got the sbatch command, and this is how you submit a regular job on the cluster. When you run it, and there are no problems in your script, it gives you back a job ID. And there's scancel, and this can be used to cancel a job that's queued or is already running. And there are a handful of other ways to submit jobs, but these are covered in the advanced training. I also want to remind you that most of these commands have manual pages available, which are accessed with this man command or with /help. So this is another one of those little videos that quickly shows you how things are working. I just wanted to show you. So there's the sinfo command, and it showed the state of all the partitions. So this main partition has all these nodes in them, and they're in various states. So in this case, the mixed state means it's got some jobs running on it, but there's available resources to run other jobs. These two draining states mean that basically there's something wrong with the node, and we're taking all the jobs off of it, so we can fix it. This mix, with code mix, and alloc means that the node is fully used, and then we can see similar for these Jupyter nodes and the high memory nodes and GPU nodes. And then there's this development partition. So it also tells you the names of the compute nodes that are available there, and the maximum time you can run jobs on those for. Yeah, I think there's something else I wanted to just show here as well. So here's an example of how you would submit a job, and then you can check the queue. I made a mistake here and I used capital U, but I left it in to show you that I'm in fact human. So I fixed it. So here it now shows that the job is in this PD state. So it's pending, it's about to run. I waited a second or two and I ran it again. And it showed that the state had changed to R, which means running. And then I canceled the job and checked the queue again, and it should then be empty. Yeah. So there we go. Oh, sorry, this CG state here is short for completing, strangely enough, but that means the job's ending after I canceled it, and then it was gone afterwards. And there was just the help page I spoke about earlier. Then there's the manual page. Yeah. So then here's an example of a job script, and this is essentially the most simple one you could possibly have. So a job script is usually a simple bash script that describes what resources your job requires and then the steps your job should do in order to process your data. So the first thing in any of your job scripts will be this shebang, this hashbang line, and that tells it what interpreter to use. And in this case, we use bash, and I expect that'll be true for almost all your job scripts. And then the next two lines, in this case, it's using the module system, which Jeremy told you about. So we're selecting, we want to use Python 3.11.2, and then we run that Python on this hello world. And that's it. We can submit this script as a job, and it will send it to a compute node and run it. And I'll show you that later. But earlier I told you that Slurm is in charge of allocating resources. And the question you might be asking is, how does it know which queue to run on, how many CPUs to use, and how much memory should be allocated? And there are a bunch of defaults for this. And this is probably the most important ones you'll be interested in. So by default, if you haven't specified anything else, the time limit on your job will be 3 hours. It's limited to using 3 GB of RAM. It uses 1 CPU on 1 node. There are various ways of specifying this, which we quickly mention a bit later. We tell it to run on the main partition, or we are telling it that's the default, and then it'll use your default account. So if you click this link over here, it takes you to a more comprehensive list of the parameters that are selectable, and you can read those in your own time. Yeah. So now we're going to write a bit more extensive job script that is a bit more explicit about what it does, and it does something a bit more interesting. So again, we have a bash script as shown by the shebang. The difference in this script is that we've added a whole bunch of these sbatch comments, which Slurm interprets and uses to allocate the resources for your job. So first off, we've got a job name. This is the name of your job. Encourage you to fill this one out, otherwise it gives it a less meaningful name. But this will help you later if you're looking at your accounting data to identify what the specific job was doing. Then we specify the time limit. So this is how long we expect a job to run for. It's a good idea to always overestimate a little bit how much time your job will take, because the speed of your job can actually vary a bit depending on how busy disks are and various other minor factors. We tend to want to be a bit pessimistic about the runtime, but you also don't want to be, you definitely don't want to underestimate the amount of time, because when a job reaches that time limit, it is killed. So you don't want it to stop before the job is running. Also need to indicate the amount of memory that your job will need. Again, these are allocated by Slurm, and if you use more than you've requested, or you try and use more than you've requested, your job will be killed, and again, you won't get your results. Again, be slightly pessimistic about how much memory your job will use. Yeah. Then it's important to specify the partition. You're probably mostly going to be using main, but if you've got a job that needs a lot of memory, we'll select high mem. If you need GPU, you'll use the GPU partition. Then we've got two different output parameters. So you've got, this is the output that if you're running interactively normally goes to your screen. There might not always be apparent, but there's normally a standard output and a standard error. But by using this parameter, you can say, because you're not running your job interactively, you can say, please put all the output from my standard output of this job into this file, and all my standard error output into this file. And this little %J here gets the job ID gets substituted in. So I'll demonstrate a little bit later what that looks like. And these two parameters are quite useful there for sending email updates to you about the state of your job. Obviously, the first one here, you've got to fill out your email address. Preferably don't fill out somebody else's email address and annoy them. And then you've got the mail type. So this is the state of your job. When the state of your job changes, these are the triggers that will to send the email. So if we've got begin here, these are all optional. You can choose which ones you want. If your job starts, so it's no longer just sitting in the queue waiting to run. Once it begins, it sends you an email. End is to send you a mail when it ends. If something goes wrong and it fails. And finally, this one is pretty useful. So this emails you when your time limit has reached 80% of the maximum that you specified. So this can be useful. So you can just double check in your job, then it's going to finish when you want. If it looks like it's going to take longer, you can mail us and request us to increase the time limit on your job, and then we may or may not be able to help you, depending on how kind we're feeling. Not really. It's depending on how busy the cluster is usually. And then finally, need to specify your account. So many people are involved in more than one project. So the important thing here is that you specify the appropriate account to run your job against. Because resources aren't free, so you are responsible for allocating your job to the right accounts. project. And then the final line here is actually it does the computation. In this case, we're using this Singularity container. It's an R container. It runs R script command, exec R script, and it passes in this hello world file to run. And then we would submit the job with SBatch. And then it'll go in the queue and it'll eventually run on the compute node. Yeah, I think say about that. So we spoke about defaults. So if you don't specify various parameters, the defaults get filled in. And I don't think you need to look at this too closely. I guess the thing to see here is that in our main partition, the bulk of the resources have 32 cores, but there are a handful of nodes with these 48 cores. Default memory for all main partition jobs is 3 gigs of RAM. And the high memory nodes, the default is 15 gigabytes of RAM. We've got this one beastly node that has 96 cores, that's and 1.5 terabytes of RAM. And this one has 1 terabyte. So yeah, and then we've got the GPU nodes, which mostly have 32 cores. Is that true? Between 32 and 48 cores. And they've got 1 or 2 GPUs on each. Actually, they might all have 2 GPUs now. I need to check that. But they've mostly got really healthy whack of RAM as well. Yeah, sorry, the other last thing I want to mention is the default wall time, which is 3 hours for all of the partitions. And then 14 days maximum wall time, except on our interactive node in this develop partition that has a maximum wall time of 5 days. Yeah. And this table might change a bit, but it'll be kept up to date on this link, which is here. It's all in our docs. We could watch this video recording of how to do things, but I'm going to risk it to do a live demonstration instead. So the first thing we do is we connect to our cluster with our SSH command. And you can see it shows you a list of your accounts. That's with you specifying your account, tells you what your default is. But you could use any of these if you've got more than one. Tells me I've got no jobs running at the moment. So I've put information in here. So in this, actually, I've got a whole bunch of files. First thing I wanted to show you was this minimal job script. And this is very minimal. It says it echoes to our standard output hello world, and to standard error it writes something as well. And this is just a pure bash script, so we can in fact just run it like this, and it outputs to the screen. Hidden behind that, this is going to standard error and this is going to standard out, but there you have it. But we do have the option of submitting this as a job. And I do that, we submit a job, we run SQ me. I wasn't fast enough, the job's already finished. We can use this scontrol command, which I didn't tell you about. We can say show job, and we say job ID. Because it's just finished running, it still works, but it tells me that the job has completed. It tells me it ran for 0 seconds because it didn't have to do much. It ran on this computer 2 node. And it's created in standard error file. So I'll look at that in a moment. Yeah, so if I look at the directory listing, we can see we've now got that file that was created. It's got this job ID in the file name. So if we look at the file, it's got both our standard out and standard error output in a single file. That's because we didn't put things in its own file. That's it. Then we get onto the more interesting job scripts. So the first one I want to show you is this Python script. So this one now, we've got, like I said before, we've got always start our scripts with what interpreter use. This is bash. Now I've given it a more interesting job name. I've told it it's going to run for 1 minute. I only need 1 GB of RAM, but now I've told it to put my standard out in this file prefixed with Python underscore module dash, and it's going to substitute in the job name into the file there. And my standard error, something similar, just the suffix is standard error, just to make it easier to understand. I've commented out these 2 lines because I don't want it sending me emails for now, but if I remove these hash spaces, then it would email someone with a bizarre email address when it begins. I'm also not specifying my account here, but it's going to load the Python module and run this hello world, which we can look at. Hello world.py, which is a very basic script, which basically just outputs the name of the user, some environmental variables from Slurm, and write something to standard error. So I'm just going to run that, and we can look at the output. That was this Python. Are we fast enough? Yes. So the job is pending. It's not running yet. It's ran, so it's finished. So now if we look at the directory listing, we see now we've created these 2 files, the standard error and the standard output. And if we look at the standard out, it's got hello me, ran on this compute node, and these are just some variables it looked at. And if we look at the standard error file, it just has a little command to that, just useful to know that. The reason you want to look at these sometimes is if something's gone wrong in your job, you can check the standard error output for interesting messages that might help you debug. So that was the Python example. Let's look at, there's a R example as well. The main difference here is that now we're using Singularity. It's got a very similar starting bit here where we just give it a different name and told it to put the output in a different file. Then it uses Singularity to run this R container. If we look at the script itself, we can see it's also very basic. It just at the end it just prints out hello, tells you the host name that is running on, and just environmental variables. Very similar to the Python one, it's just formatted slightly differently. So we can run that script like that. And it's running, it's in the state R, and by now it's finished. Oh, it's not. Oh, Singularity can actually take slightly longer to run because when it loads the container, it sometimes has to set up the software first. So it can be slightly slower to start running, but the run times in the end tend to be very similar to if you're running software through, say, a module. So our job is run. Check. We've now created these 2 files here. So our standard output and our standard error. Look at the standard output first. Very similar. Tells you which compute node it was running on. It says hello. And then our standard error file is that one. I didn't even write anything to standard error. And that's mostly what I wanted to show you in this demo. So we can go back to our presentation. Just a quick note on best practices. So really remember, this is a shared resource, the ilifu cluster, so it's not just for you. We've got a bunch of bioinformatics and astronomy users all trying to finish their theses and publish interesting papers. So we have to be very responsible about our resource usage. A quick list of do's. So you must try and use sbatch for production work. We haven't shown you interactive jobs in this session really. But for the most part, please use sbatch. You must identify your resource requirements. This includes the number of nodes that you want to use, the cores per node, the amount of memory you need, and your expected runtime. Very important is to try and clean up your temporary files. Normally, you put these in a scratch3 directory. That scratch3 tends to fill up very fast, and it's a hassle if it gets full because then nobody can run their analyses, simulations. Yeah, and please use Singularity containers for software. You can't install software directly on the nodes. And you can always send us requests to either build you a container or create a software module. And then this last one is about use the transfer node for data transfers. That comes in a later presentation. And that's important for those of you familiar with, say, SCP or rsync. Don't do that to the login node. You've got to use this transfer node. A couple of things to avoid. Do not run big processes on the login node. Don't place large files in your /users or home directory. Those should rather go in your projects or the appropriate place under /cbio/users or /ilifu/users or /idea/users. Yeah, don't use SCP rsync on the login node, and try not to request more resources than you really need. So try and be as accurate as possible. Sometimes a bit pessimistic about, say, your RAM and your wall time. CPUs you can normally be pretty accurate about. Then, yeah, so if you follow these guidelines, you can make use of the cluster and ensure an efficient, hassle-free experience for all. Thank you very much for your time. Just a reminder, you can always contact us on the support email address, and our docs are available, docs.ilifu.today. Yeah, that's it for me. I think we can probably take questions.
Cool. Thanks, Dane, for the presentation. Yeah, we'll open the floor to questions. If anybody has any questions about the material or any kind of issues related to the material, you're welcome to post in the chat. You're also welcome to raise your hand and we can take questions over the mic. So I see we have one question. Please do correct me if I make any name pronunciations incorrectly. Cool. So John Harvey has asked, where can one access a list of currently available software containers similar to the modules? So we do have, let me share my screen. We do have some information available in our user documentation. So unfortunately, it's not very full or complete. It's quite difficult to keep a record of all the software because of the number of containers that we provide. Sorry, under software environments, available containers here. So these are the most commonly used ones. I think these are somewhat updated. So there's and this is also a caveat. This is all astronomy specific containers. There's two flavors of Casa, which is modular, which is how they're installed with Python. And then there's also Casa stable, which is the also I think they call it the monolithic Casa, where Casa is wrapped in its own binary package. So if you click on these arrows, they drop down menus and they can provide information about the libraries and different things that are included in the container. There's the AstroPy containers. So these have a very large suite of astronomy specific software all bundled into a single container. So you can come and check here if a container includes the software you're looking for. Similarly, the GPU containers have there's a TensorFlow and a PyTorch flavors of the GPU containers. So this is a resource, but it's not complete. If I should have shared my terminal at the same time. Give me 1 second. It's a very good question. The other options, so here we also detail in the documentation these steps, but basically how to know if a software container includes the software that you need. So the options are to firstly the name of the container will generally have the primary software in the container. You can run Singularity run help on a specific container, and this will output the help information, which sometimes has a description of what's included in the container. Other options is running, if it's Python based, you can run Singularity and the path to the container and just run pip freeze, which will print out the Python installed packages. And then the other option is you can check the build script of a container. So you can run Singularity inspect -d will show the build script. So I'll just do a quick example of this. You can't run Singularity on the Slurm login node, but you can run, for example, it as part of a quick job. So if I do srun and then I do idea software containers, is it not auto completing? So let me just give an example of the idea software. It is a very long list of software, but basically you can view the individual containers will indicate by their name what software they include. And then I'm just gonna give an example of where's Sophia is a frequently maintained one. So here I'm just gonna run Singularity. So that's printed out the build script, and here you can look at the specific build script of this. So if you're looking for Sophia, for example, you can see it's built with Ubuntu, and it'll include Sophia 2, Sophia X, other things like image magic, that kind of thing. So it's quite difficult to always see what's included. The other option is to email support and say, I'm looking to install this software. What is it available in a container? And then if not, we can advise and build it for you. Yeah, it's one of the more difficult components of the record keeping to indicate what software is available if it's not in a module. But yeah, there's a couple of tools that are useful for users for checking where you can find software. Yeah, so if anybody has any other questions, welcome to post to the chat or to raise your hand and unmute yourself. We're going to be doing the next session next week, Tuesday, on the 3rd of March. So in that session, we're going to be covering software environments, specifically the virtual environments using Python. And we'll also cover using RStudio. So you're able to spin up an RStudio session using ilifu resources. So we'll demonstrate that. And then Theo will also take us through more advanced Slurm uses. So where Dane showed sbatch, which is really the primary way we would want users to make use of the Slurm cluster, because it's basically the most efficient in terms of scheduling. But Theo's going to take you through interactive jobs. So those are useful for development and testing and debugging. And he also take you through some other advanced job structures and how to view information about your previous jobs. So we'll be doing that next week, Tuesday. So hopefully we'll see you all there again. Yeah, so I think if there aren't any further questions at the moment, if you do think of something that you want to ask, please email us at support@ilifu.ac.za. Otherwise, we'll see you next week and we can address any of your questions there as well. It has been a long session, so I won't keep you all here. Thank you again for attending. We really appreciate that you take the time to attend the training and get familiar with how to use the cluster and the best practices and stuff.